Okay, this is part 2 for solving differential equations in a form of a system. So we had a system of differential equations. We look at, I think, example 5.5 in the textbook. It's the reaction rate with 3 species. So in the last lecture, I was covering the comparison between the species or the concentration of the species at different times. So this is again the same plot. We have the concentration against time for 3 different species, A, B, C, 2 different dt values. So the first set of 3 correspond to dt of 0.1, and the last 3 correspond to 0.01. And I was comparing let's say brown and green. So brown and green, right? So green is less accurate because it has a larger dt, and brown is more accurate because it has a smaller dt. So from green to brown, the result is more accurate as we go up here. Same thing here as we go down. This one is the same thing as we go up from light pink to dark pink, right? So from light pink, dt 0.1, to dark pink, which is 0.01, this result becomes more accurate. So this is the error we're making. This is the error. So this much is the error we're making when we have this dark curve. From dark to light curve, our solution becomes more accurate. And same thing with the dark blue and light blue. So this is less accurate, this is more accurate. And the result becomes more accurate as we go down or increase or decrease our dt. All right, I think that's enough. So this was example 5.5 of the textbook, how to solve a system using forward Euler. So in the next example, I'm going to look at high order derivatives and how we can convert it into a system. So let me close that. Okay, and so we're going to look at converting a higher order differential equations to a system of differential equations. So by higher order, I mean so far we only look at the first derivative of y with respect to t equals something. Like the generic form we started actually from the beginning of this chapter was first order differential equation, right? So first order. So that means we have only the first derivative of y with respect to time. Now what if we have second order derivative of y with respect to time? Then that's what I mean by higher order. And okay, so this is section 5.6 of the textbook. Okay, we have a second order differential equation. We have a second derivative this time. I don't have, well, I may have first derivative as well, but the first derivative and everything else goes on the right side. I only have the second derivative on the left, and everything else I like to see them on the right, and that's what I have right here. This is the form. Because that's second derivative, we need to have 2 conditions. One on y and the other one on the derivative of y. Okay, so y naught is y naught, and y prime at 0.0 is y prime naught. Okay, so the way to solve this is the following. We bring in a new variable called z. Okay, we're going to rename the derivative of y with respect to t. We're going to rename it as z. So z is going to be the first derivative of y with respect to t. Okay? Then we're going to write this equation in terms of z. If the first derivative of y with respect to t is z, then the second derivative of y with respect to t would be the first derivative of z with respect to t. Because z is dy dt, then dz dt becomes d squared y dt squared is the second derivative of y, right? So then by having this new variable z, I can rewrite my equation in 5.33 to 5.35. So this becomes dz dt, now it's first order, but it's in z, is equal to function of y, and then we don't have y prime anymore because y prime was named z. So I have replaced y prime by z here. Okay, so it's f of y, z, and t. Okay, this looks like a first order, and I know the technique to solve that using forward, backward Euler, trapezoidal method, RK2, RK4. All of these are for first order method. And as long as I have a first order differential equation, I should be able to solve it. Okay, now the way we solve this is the following. Now we have two variables to solve. One is the z, and the other one is the y. And we have to solve this system. Looks like we have a system, right? This is one equation. dy dt is equal to z, it's first order in y. And the second one is dz dt. And this is also first order, but it's in z. Okay, I have two unknowns to solve. The z that I introduced, and the y, which is the original variable of the problem. Okay, now this is a system with two conditions. One is y at point 0 is y naught, and the other one is z at point 0, which is y prime, right? We know this from before. This is z at point 0. Okay, so two equations, two unknown. That's pretty much like a system. I should be able to solve it. Let's look at one example. This is example 5.6. Okay, I have a differential equation like this. And this is the equation, the governing equation for the motion of, you can think of a pendulum. So if you have a pendulum that goes out of equilibrium from left to right and back to the original location, right? And the oscillation of the pendulum is governed actually by this equation. You can think of y as the angle between the pendulum and the vertical line, and theta is, you can think of as a t. That's the time variable. Okay? So in other words, if I have, let's see if I can draw a pendulum here. Okay, so I have, let's say pendulum, and I want to make this dashed line and make it thinner, even thinner. Okay, maybe that one. Okay, let's say I have a pendulum, and my pendulum starts from, let me add another line here. Okay, and make this one solid line. Okay, I don't want that. All right. So there's, let's say I have a pendulum like this, and I'm going to put a mass or a circle at the end of it. Okay, let's make this one a bit smaller, like that. I'm going to move it to here. Let's say this is a pendulum. I move this pendulum from, this is the equilibrium position. If I put the pendulum here, the pendulum doesn't move, right? But if I move the pendulum up to here, and then let it go, then it's going to go back to here, and then it's going to bypass this point. It goes up on the other side, then it's going to oscillate back and forth, and back and forth. Let's call this angle y. This angle is going to be y, and then the time variable is going to be theta. So this equation would be identical to the dynamical equation of an oscillating pendulum. And the question is, can I find the location of this pendulum on the angle as a function of time? And that's what we have to solve this differential equation. So let's see how we can solve this. To solve this, you see that that's a second order differential equations. We have to rename the first variable. So I'm going to call, let's think of it this way. Theta is a bit misleading. I'm going to just have this as t, right? And then, so we can, as the book actually puts it, so we can divide through by tau. Let's say tau is a constant, because c is also a constant. We can divide by tau, and then assume that theta by tau is a variable like time. And then I can easily convert this equation to the second derivative of y with respect to t, 2 zeta, or 2c times derivative of y with respect to t plus y is equal to, let's make life simple and put 1 on the right hand side. This is just one equation, right? It is a specific case of this generic one, but doesn't change our technique. So actually to illustrate that our technique works for any differential equation like that. Anyway, so let's say we have this second order differential equation. I want to solve y with respect to time. Okay, so we're going to rename dy dt as before, like z, and then with the two initial conditions that we have, one is going to be y at point 0 is y naught, and then the second one would be y prime at point 0. Let's call it z naught. Okay, so with this definition, we can rewrite this equation in terms of z. So z, where z is dy dt, so the second derivative of y with respect to t would be the first derivative of z with respect to t. Okay, and I move the rest of it to the right side, so the right side becomes 1 minus, so minus 2 zeta times dy dt is z, so here's 2 zeta times, or 2c times z, and then minus y, so here's minus y. Okay, now I have two equations to solve for, 1 and 2. Looks like a system. I have to solve for y and z. I can go ahead and do forward Euler on each, right? You can do forward Euler on each and solve for y and z. So let's look at spreadsheet calculation. Here is the spreadsheet version of it, and I put the equation side by side. Okay. So let's see how we can solve this system using spreadsheet. Okay. So I'm going to discretize this using forward Euler, just to let you know that still we use forward Euler because that's simple, but we know that it's less accurate. It's okay, as long as you know how to do forward Euler, I think you should be able to do it using the trapezoidal rule or RK2 or RK4, the more accurate methods. Okay, so if I discretize this equation using forward Euler, that's going to be yn plus 1 is going to be yn minus dt times zn. Okay, the right side should be always at the current state, that's at point n, and this one is discretized at n plus 1 minus yn, which I just moved around. Okay, the second equation is right here. It's going to be z at n plus 1, that's equal to z at n okay, and then plus the, I'm sorry, this should be plus, okay, that's plus dt times whatever it's in here at time n. So it's going to be 1 minus 2 times c times z at point n and minus y at point n. That's it. So two equations. I have two equations, two unknown. Unknowns are yn plus 1, zn plus 1, with the initial condition of y0 is this and z0 is that. So let's create two columns, one for y, one for z. Here's the time. Our time goes down with the increment of 0.1, that's dt. Let's say our zeta or c, whatever I call it here, let's call it c. This is c. Okay, so the c is that, 0.1. Initial condition, we have both 0 here, 0 here. Let's say, well, now y naught and z naught, both of them are 0. I put 0 here. And then the only piece actually is, all you need to do is these two cells. If you correctly implement these, the rest is just dragged down. So what is y naught? Sorry, what is yn plus 1? This is yn plus 1, right? So yn plus 1 is going to be yn, so I'm going to click on that. And, shrink this a little bit. Okay, it's going to be previous y, which is blue cell, plus dt times zn. And dt is green cell times zn is the purple. It's pretty straightforward. What is zn plus 1? Well, zn plus 1 is going to be previous z value, which is blue cell, that's blue cell, plus dt, which is green, right? Green times 1 minus 2 times, see the purple cell, and then times zn, which is the blue cell here, zn, and then minus yn, which is going to be the brown cell. So I implemented the second equation right here, and there you go. You highlight these two, double click, done. So here's the solution of differential equations. We solved second order by just converting into a system. Now we can also plot. So here's the plot of y against time. And if you think of this as a pendulum again, you see that it oscillates up and down. So it starts from 0, and then up, and then down, and then up and down. But you see that the magnitude is decreasing. So initially goes to a higher peak than the second peak. Second peak is a bit lower. And if you increase the time, you can see that actually the peak still goes down and down. Alright, so that was solving a second-order differential equation. Stay tuned for the next video.